All right, let's look at another one. Measure pressure. This is what the Muppets use to measure pressure, a manometer. Manometer, yes. Okay, so a manometer is basically this thing that we built over here. This is essentially a manometer, except you can't really measure anything with it, but it acts like a manometer. All right, so let's look at that, and let's draw that. Let's draw a manometer. So again, we have some vessel in which we want to measure the pressure here. It's bigger than that, though. We have a large vessel. We want to know its pressure. So you connect it to a tube like this, and then the tube goes way up in the air like that. Ooh, manometer like that. La, la, la. And at the top of the manometer, you have atmospheric pressure. So it's open to the air. Okay? Open to the air, and you've got a fluid in here, you know, just like we have a fluid in there. So if this is an atmospheric pressure and this is an atmospheric pressure, what is the fluid going to do? It's just going to sit there, just like this one is. And the meniscus is going to be at the same height, because that has atmospheric pressure on each side. Okay? But I'm not going to draw that. That's the boring case. Now, what if the pressure goes up here? So what if it goes bigger than PATM? It's going to push the liquid down over here, and it's going to push it up over here, like that. Okay? And then the measurement you make is basically the difference between these two. All right, that difference, D. All right, so manometer, pressure pushes liquid column. I'm going to say by D. Okay, I'm not going to say up D or down D. It's really it's the net effect is D. Just like in the problem I did over again. I said really it's the difference in the heights is D. We won't worry about which one moved up so far, which one moved down so far. That has to get into gases and stuff. Okay? What you care about for this class is how am I going to relate that D to pressure. All right? So as I said, everything we do today will be the hydrostatic equation. Rather than a change in pressure, wouldn't you get a change in volume? Okay, so it's a good question. Here's the deal. Remember, this is a liquid, and liquids are incompressible. So you don't get a change in volume. There we go. So that green thing there, when I pressurize one side with my manometer attachment, so now I am the large high-pressure vessel. Right, so you can see that it doesn't compress, right? It stays the same volume. Oh, it's separated. Oh my God, okay. So yeah, so liquids are incompressible. The gases are compressible, which is why we don't get too deep into the volumes of everything going on. We don't want to do the volumes of the gases. That's why we didn't get too deep about how much we're moving those. But no, the liquid's incompressible. That's critical, right? If we don't have that, then this whole thing doesn't work. Okay, so now we want to figure out the relationship between D and the pressure. We're going to use that equation. That equation requires you to look for the pressure at one place and know the pressure at another place. This is exactly this, right? Where do we know the pressure? We know atmospheric pressure. We know what it is here. Remember, gas is not very dense, so therefore the pressure here is the same as the pressure here. The weight doesn't matter. So we know the pressure there, and we need the pressure here. Right? Why there? Because that's D. That's the thing we're measuring. That's how deep we went. So then you could say, let's apply the hydrostatic law here. Let's say the pressure here, there, equals the pressure at the top of the column, P ATM, plus rho GD, right? The density times gravity times that. And then you could make this question again, similar to this question, is what are we really getting out of this thing? What really equals the displacement? D. Oh, well, you got to pull this over here. And you say what we're really measuring is the absolute pressure minus the atmospheric pressure. So again, this is the gauge pressure. it's not measuring the absolute pressure that I blew in there. It's measuring the pressure I blew in there minus atmosphere, because atmosphere is everywhere. So the proper words, I guess I should have said before, this is absolute. And then together, they make the gauge pressure. All right? So all you got to know is that P absolute equals P gauge plus P ATM. If you're having trouble getting it in your head intuitively yet, that's okay, but just have this equation ready. Always be able to jump around. That's absolute ABS. So I could say, if I wanted to calculate the actual force being applied to the walls on the inner surface of this chamber, which one of the three would I use? That would be absolute, right? There's the actual pressure in here is the absolute pressure. But I said I want to calculate the net force on the walls, do the pressure inside and outside. Then I would say, well, I got to take off the atmospheric pressure because the absolute's this way minus the atmospheric. Oh, yeah, that's what gauge pressure is. Which was going to affect when the tire actually explodes? The gauge pressure, right? The other two are just compressing the material. They're not making it expand and blow up. So that's why we care about the gauge pressure. It's like usually the one that matters. All right. Let's see.